PAM250 will represent sequences that are highly divergent, and the mismatches would not be so strongly negative score in a score. Okay, so if you look at the PAM250, this is PAM10. Okay, this is PAM250. So you can see that compared to PAM10, the mismatches do not have such strongly negative scores. Okay, less negative. So which means that when you are going to use PAM250 for sequences that are highly divergent, the score would not be such a negative score. Okay, it not be strongly negative. It may still be close to 0, may still be maybe -1 something, but will not be highly negative. That would lead to a conclusion that they are not related. So that is why if you have sequences and you know that they are divergent sequences, then you should be using a matrix that represents that level of divergence. Okay. PAM1, so PAM250, for example, I showed you the alignment of two sequences that were highly divergent. You remember those sequences? Beta globin and myoglobin. So, how many identities? 16% identities, and rest were mismatches and gaps, right? So, if you are going to use PAM1, you have strongly negative scores for mismatches. So, it would be a highly negative number that will come out when you will compute the score for the alignment. So, you will infer that they are not related. Okay. On the other hand, it used some matrix, and that was Blossom 62. I am going to come to that. On the other hand, if you are going to use PAM250 or higher number PAMs, then the scores would not be such a negative score that you would outrightly infer that they are not homologs. Okay. So that is the reason. So that is one example. And I showed you some examples. For example, ubiquitin, right? It's highly conserved. I also showed you another example. So let's go back to examples, and you can use the examples from here. So yeah, ubiquitin. So in order to score the ubiquitin sequences, which matrix you would want to use? PAM1, right? Because these are highly similar sequences. You would want to use the matrix that reflects the expected divergence of the sequences. Okay, and highly similar, so PAM1. Highly dissimilar, PAM250 or higher PAMs. Okay, clear? What cutoff? Yeah, not quite in that sense actually. For example, here it is 99% identities. So it corresponds with PAM1, right? PAM1 is also 99% identities, 1% divergence, right? So, but in general, this is not known, because you have sequences you don't know how similar and how dissimilar, because that is inferred after you have done the alignment, right? This is a challenging question. People would want to use one of these these matrices in order to infer whether the sequences are related or not. So the best way to approach this problem is to use all these different PAM numbers, maybe PAM1, PAM100, PAM250. So few PAM numbers. Okay. Now suppose that you have two sequences that are highly divergent. Okay. When you will use PAM1, then strongly negative score, right? When you will use PAM250, the score may come out positive, right? So then you will say that it seems like that these sequences are indeed related, but they are highly divergent, right? So it is just not possible to find a matrix that is appropriate for scoring the alignment of two given sequences, because you don't know actually a priori that these sequences are highly similar or highly dissimilar. That is inferred after you have performed the alignment and the score, right? After scoring and after aligning and scoring, you know it. So it is better to use multiple PAM matrices, different number PAM matrices, and then look at the scores, and based on that you infer whether the sequences are closely related or distantly related. Okay, first you would infer whether the sequences are related or not. If related, then closely related or distantly related. Okay, think about random sequences. When you align them, you will get some identical residues that are aligned against each other, same residues aligned against each other. You will get some score. Okay, but if you compare with alignment of homologous sequences, then the score from random would be lower, right? Because you would expect the similarity score from related sequences, sequences that shared a common ancestor at some point of time, to be higher than the scores coming from alignment of random sequences. Okay, and that is what is being signified here. If you look at the score formula, so I think that comes next. This one. Okay, so the numerator is this one. Qij is the probability that residue I is aligned to residue j due to relatedness, and Pij is the probability that residue I is aligned to residue j just by random chance. Okay, so basically what you do, if you are given sequences that are homologous sequences, then you count. For example, you have considered residue I and residue j. You count how many times you observe in the alignment that residue I is aligned to residue j, okay, and divide by the total number of aligned positions. That is the probability that residue I is aligned to residue j by relatedness. Okay, then you just randomly reshuffle the residues in the homologous sequences. Okay, just reshuffle, then that becomes random alignment, right? Or you generate random sequences and align them, or here you can just randomly reshuffle the residues in the alignment. What you will get is random alignment. Okay, and then compute the probability that residue I is aligned to residue j. And now imagine that you have two sequences that are highly similar. Okay, so you have residue I aligned with residue I itself so many times, right? Because they are highly similar. So you have tons of identities in sequences that are highly similar, region that they have evolved recently, right? They are related and they have evolved recently, so highly similar. When you will randomly reshuffle, then there would be very few instances that you will see that residue I is aligned to residue I in the alignment of random sequences, right? So what will happen, that the numerator will be higher, much higher than the denominator. Okay, so this ratio would be much greater than 1, right? Because numerator would be much higher than the denominator, so the ratio would be much greater than 1, which means that the likelihood, this is likelihood that residue I in sequence A is aligned to residue I in sequence B due to relatedness is much higher then observing them aligned in random sequences, and that is going to help you in infer that these two residues or sequences are related by ancestry, right? Clear? Okay, so this formula is this is the whole idea of this formula. Okay, so let's so this is what they did. Dehoff et al. They derived a matrix based on sequences that were highly similar to each other. Okay, which means that the score for matches or identities were strongly positive, highly positive numbers. On the other hand, scores for mismatches were strongly negative numbers. But the problem was that when that matrix was used for scoring sequences that were highly divergent from each other and yet arising from a common ancestor, the overall score, the similarity score for the alignment was so negative that they were just rejecting the hypothesis that these sequences are related. Okay. So, and that is the reason PAM1 was extrapolated to longer evolutionary times, because PAM1 was not appropriate for scoring sequences that evolved a long time ago. Okay. So, and because of the lack of protein sequences at that time, because this was developed in 1960s, there were a handful of protein sequences at that time. So, only highly similar protein sequences were used for deriving PAM matrix. Then a mathematical model called Markov chain model was used for extrapolating the matrix from PAM1. So, first they derived PAM1 representing highly similar sequences to longer evolutionary times. So, PAM100, PAM250 and so on. And then those matrices were used for inferring whether the sequences are related or not. Okay. So, typically you are going to use all these different number matrices. So, PAM1, PAM10, PAM50, PAM250, and then look at the values. And based on that, you infer whether the sequences are related or not, and if related, whether they are closely related or distantly related. Okay. So, there is no such approach actually where you are given two sequences and you will be able to decide whether you are going to use PAM10 for it or PAM100 for it or PAM250. You do not know actually, because you do not know the similarity or dissimilarity between those, because that is what you are doing. You want to know it using these matrices. So, so you would want to use different number matrices, and then based on those values you will infer. Maybe I think one of the questions in tutorial that should help you when you work on that. Okay. But by 1990s, hundreds or thousands of sequences were already obtained. Early 1990s, sequences from many different protein families. So, researchers wondered that why we would want to use PAM matrices, higher number PAM matrices, when there are sequences from protein family where members of protein family could be closely related as well as many could be distantly related. So, why not use the evidence that are there in the protein families rather than using mathematical model to extrapolate to longer evolutionary times, because biological sequences may not be exactly following any mathematical model. Okay. So, that is why in early 1990s, Blossom matrices were derived, and they were derived based on the sequences of the protein families. So, the whole idea was to use the sequences in protein families that were both closely related and distantly related. They are from the same family, so it was known a priori that those sequences are all related, whether they are highly similar or highly dissimilar. This information was lacking in 1960 when Dehoff et al. Dehoff and colleagues were trying to derive these matrices. In 1990s, we had enough information. So, we had information about sequences that were similar, of course, as in 1960, and also sequences that were highly dissimilar yet were related. So, we got that information by 1990. So, Blossom matrices were derived around that time based on these data that were available by early 1990. So, the whole idea was to align the sequences in protein families and then extract the ungapped regions from the alignment. Okay, so just discard those regions that have gaps, only extract the regions that have no gaps. Okay, and then those sequences were clustered. They were grouped together in clusters. Within clusters, the sequences were L% or more similar to each other. Think like L is equal to 90. So, 90% or more similar to each other. And following this, the comparisons were made across clusters. So, across clusters, there were sequences that were 90% or less similar to each other, right? Because within cluster 90% or more similar to each other, across cluster 90% or less similar to each other, and the scores were derived based on across cluster comparison. Okay, so this way, for example, if you look at Blossom L, for example, and I said L is equal to 90%. Okay, so when Blossom 90 is derived, so it is derived across cluster comparison, which means that it represents sequences that are homologs but are 90% or less similar to each other. Okay, and then the probabilities were computed. The probability of residue A aligned to residue B, QAB due to relatedness, and probability PAB due to random chance, and then you can compute the score for the alignment of residue A with residue B. Okay, but using the across cluster comparisons. So, sequences that were present in two clusters, so pairwise. Okay, and because within cluster you have sequences that were 90% or more similar to each other, across you had sequences that were 90% or less similar to each other. So, this way Blossom 90 was derived, which represented sequences that were 90% or less similar to each other. Okay. So, and similarly all these different Blossom numbers. So, for example, Blossom 60 represents sequences that are 60% or less similar to each other. Okay. So, this way different Blossom matrices were derived and they represented some level of divergence between sequences that were related due to ancestry. And currently Blossom 62 matrix is used, and what Blossom 62 matrix represents. So, the default matrix in BLAST is Blossom 62. So, what Blossom 62 represents? 62%? Yeah, 62% or less, not just 62%, 62% or less similar to each other. Okay. So, not similar, not highly dissimilar also, right? And that is why Blossom 62 is a good compromise, because a priori you do not know whether the sequences of your interest that you want to align, how similar or dissimilar they are. So, Blossom 62 was found to be very good for scoring the alignment of sequences that were highly similar, as well as for sequences that were moderately dissimilar. Okay. It may not be good for sequences that are highly dissimilar, where you would want to use higher Blossom numbers or lower Blossom numbers. For sequences that could be highly dissimilar to each other, yet they are related, which Blossom matrix you would want to use? higher number blossom matrix or lower number blossom matrix? Lower number, right? Because lower number represents more divergence. If you consider, for example, blossom 1 represents sequences that are 1% or less similar to each other, so highly dissimilar. So if you consider both PAM and blossom matrices, the numbering is relationship is reverse, right? So higher number PAM means more divergence. On the other hand, higher number blossom means more similar, low divergence, right? So it's reverse relationship. So very good. So lower L values correspond to longer evolutionary time in blossom. So here is blossom matrix. So these matrices were used for scoring the alignments. But the challenge was, okay, you are given the matrices and then you can score the alignments. So given two sequences, there could be many ways to line up, right? And once you have lined up, you can compute the similarity score for the alignment. But remember, because there could be so many lineups, possible lineups of two sequences could go exponentially very high, it is just not possible to score each of these alignments. It will take, if you do it naively, it would take many days or many months even to score the alignment of two sequences that may be just 100 residues long. Okay, so it is just not possible. Even a modern day computer will struggle to align all these all possible alignments of two sequences and yield you the alignment that has the highest score. So that is why computer scientists, they worked on in developing algorithms that can give you the optimal alignment without performing the scoring for each of the alignments. Okay, and those algorithms are called dynamic programming algorithms, where you don't have to literally, as I said, that you have to align each, if you have to score each of the alignments and then select the alignment which gives you the highest score. So you don't want to do it because it is practically not feasible even for shorter sequences. So dynamic programming algorithms have been developed that can help you in obtaining the optimal alignment without performing each of these computations for alignments. Okay, so we will get to that in a moment. So there are two types of sequence alignment. One is global and the other is local, and we discussed about it. So we will first consider the global alignment algorithm developed by two scientists, Needleman and Wunsch. So it is called Needleman-Wunsch algorithm, also global alignment algorithm. And the second algorithm was developed by Smith and Waterman, and this is for local alignment. Okay. Okay, so there are three steps to global alignment. The first step is set up a matrix, the second is score the matrix, and the third is find the optimal alignment. Okay. So let's look at the alignment of, so just these are some examples to help you understand the dynamic programming algorithm. Okay. So we will go step by step. Let's consider two sequences, DPLE and DPLE. So same sequences, and you want to align it. So the first sequence DPLE and second sequence DPLE, it is easy to align. You will say that, okay, D aligned to D, P aligned to P, L to L, E to E, right? Straightforward. So how to represent this in the matrix notation? So let's say that sequence 1 is on the side, sequence T is on the top, and then you start putting say a star or asterisk for each of these residue alignments. So D aligned to D, so a star here. Okay. P aligned to P, a star here, and join it. L to L, this one, and then E to E, this one. Okay, all stars. So when you have matches, all these are matches, you come in the matrix diagonally, right? Diagonal. So diagonal means match. On the other hand, if you see that if there is a mismatch, so sequence is DPLE and second sequence is DPME, so there is a mismatch in the third position, LM substitution. If you want to align it, you will align like this, you may align like this. So D aligned to D, P aligned to P, L to M, E to E, right? You will tolerate one mismatch, it got aligned. And then do similarly. So you will see that for mismatch also, you come along diagonally in the matrix, okay? But now let's consider two sequences. First sequence is DPLE and second sequence is DPE. And I am asking you to align DPLE with DPE, okay? So you may be tempted to put a gap. So D aligned to D, P aligned to P, but after that you do not have L here, L is missing, and then you have E and E which you want to align, right? So D aligned to D, P aligned to P, and you may be tempted to put a gap for L in sequence 1 aligned with a gap in sequence 2, right? And then E aligned to E. So, and let's see how this can be visualized in the matrix. So, D aligned to D star here, P aligned to P star here, so diagonally. But then L is aligned to a gap. How this can be shown in the matrix? Vertical, right? So which means that, okay, you move from residue P, yeah, you can come here. You move from residue P to residue L in sequence 1, right? So move from residue P to residue L in sequence 1, but you remained at residue P in sequence 2. And this can be showed by a vertical line, right? You move from residue P to residue L, but remained at residue P in sequence 2, and this is represented by a vertical line in the matrix, okay? And then E aligned to E, okay? So which is a star here, you come diagonally in the matrix. Clear? Clear? So now remember, if I only give you this matrix and I will ask you to construct the alignment, then you will follow the rule that I just discussed. Okay, so I am here, I am tracing back. So I am here. So this is which move? Diagonal. So diagonal means match or mismatch. So you will going to go, you are going to see, so you are in this cell, you are going to see which residues are there. So in sequence 1 it is E, in sequence 2 it is E. So E aligned to E, okay. So now I am here, okay. So, okay, how did I come here? I am backtracking. How did I come here? Diagonal or vertical or horizontal? Vertical. And vertical means, then you will look at the vertical. Vertical means that you move from P to L in sequence 1, but you remained at P in sequence 2. The residue that you move to should be aligned to a gap, right? So the residue that you move to is L in sequence 1. So L in sequence 1 should be aligned to a gap, okay? And then now you are here, it's diagonal or vertical or horizontal? Diagonal. Diagonal, and then you have the residues P and P. So in this cell, P and P, okay? So you will P and P align to each other, okay? Diagonal means match or mismatch. Vertical or horizontal means gaps. Okay, very good. So now remember this, and this will help. So now we are learning dynamic programming algorithms, and dynamic programming algorithms were developed for alignment of sequences more efficiently than doing naively, because it was just not possible to score each of the alignments of two given sequences, because it was computationally so demanding that even modern day computer cannot do it. So that is why this algorithm was developed, and the whole idea of this algorithm was to use a function, a recursion function, which computes the best score up to alignment position I in best score up to position I in sequence X and position J in sequence Y. You want to align two sequences X and Y. Fij is the best score up to position I in sequence X and position J in sequence Y. Okay, remember. And the whole idea of dynamic programming algorithm was to obtain the best score up to position I in sequence X and position J in sequence Y from the best score one position back and increment it by the match that you observe. So, score for match or the score for gap. So, you will see this. So, now consider this best score up to position I in sequence X and J in sequence Y. So, there are three scenarios. So, best score up to position I in sequence X and position J in sequence Y. Okay. So, one scenario is that Xi is aligned to Yj, right? But there could be other scenarios where you will say that because we consider insertion and deletion, so Xi can be aligned to gap, right? And Yj can be aligned to gap. So, when you consider alignment up to position I in sequence X and J in sequence Y, then there are these three scenarios. Xi is aligned to Yj, that is the first scenario. Xi is aligned to a gap, second scenario, and Yj is aligned to gap, third scenario. Okay. Okay. So, as I said, the main idea of dynamic programming algorithm was to obtain the best score from the best score one position back. So, which means that you are here and I and J are position indices. Okay. So, what would be position indices one position back for this scenario? So, Ij current, one position back indices would be, I'm sorry? No. So, these are three scenarios. I am saying that just consider this one where Xi is aligned to a gap. Okay. So, Xi means that this is ith position in X and this means this is jth position in Y, right? Now, one position back, what are the indices? So, indices here are I and J, position indices. One position back, the indices will be, okay, let me say, okay, I am saying that I is 10, okay. So, this is the 10th position in sequence X and I am saying that this is position number 20 in sequence Y, okay. So, now I go one position back. So, okay, so what would be 9, right? And this would be 19. So, you will say I minus 1, J minus 1, right? So, the best score up to Ij can be obtained from best score one position back, positions are I minus 1, J minus 1 and increment it with the score for Xi aligned to Yj, right? So, let us look at this. The best score up to first scenario, the best score up to position I in sequence X and J in sequence Y can be obtained from best score one position back. Indices are I minus 1, J minus 1, clear? F is the best score and incrementing to it the score for alignment of Xi with Yj, okay, the first scenario, Xi is aligned to Yj, okay. And now consider second scenario. So, this current position is I and then this is gap, okay. So, one position back, what are the indices? I minus 1 and then J, yeah, I minus 1 and then this is J and increment it with the score for Xi aligned to gap is gap penalty, right. So, that is a gap score. You can say gap creation here, okay, you can say it, yeah, but we do not know actually, let us say right now just say gap, okay. So, gap So this is second scenario. So best score up to position X, up to position I in sequence X and J in sequence Y can be obtained from the best score one position back for the second scenario. Indices are I minus 1 J plus the gap penalty. A gap is negative, that's why negative is shown here. Okay. The third scenario is Yj is aligned to gap. And what are the indices? Indices are I and j minus 1. Ij minus 1 and add to it the gap penalty, okay, which is this one. Ij minus 1 and add to it gap penalty. So this is the recursive equation which is going to help you in finding the best score up to the alignment at certain position in X and certain position in Y. Okay. So you have these three values that will be computed, and then you select the best out of these three, and best is the maximum. Okay. Okay. So and let's consider that the scores are as follows. For match it is plus 1, for mismatch it is minus 2, for gap it is minus 2. Okay. So just very simple scoring scheme. We are going to use this. So let's show this in the matrix notation. So consider sequence 1 on the side and sequence 2 on the top. The indices are I for sequence 1 and J for sequence 2. And if I say that this is I, then this would be one position back, this would be I minus 1. And if I say that this is J, then this would be J minus 1, right? And I am going to fill all these cells by the best scores. So this would be Fij. So best score up to Ij. So this was J and this was I. So this is Fij. Okay. And then this would be this is I minus 1, this is J. So Fi minus 1J. And this is of course Fi minus 1 J minus 1. So this is I minus 1, this is J minus 1, and this one is Fi and J minus 1, right? You fill these up. And then let's consider the first scenario, this one. So from Fi minus 1 J minus to Fij, okay? So Fi minus 1 to J minus 1 Fij, and this is diagonal. Remember, this is match or mismatch, right? Match and mismatch, you come along diagonally, so this is diagonal. On the other hand, these two are gaps, and for gaps you come along vertically and horizontally, right? So vertically and horizontally. So this one is the second scenario. Xi is aligned to gap, so which is shown in the matrix notation like this vertically. And then the third scenario, which is Yj is aligned to gap, which is this one. You get Fij from Fij minus 1, which is the horizontal move. Okay, clear? So these three. So these three, and then you select the best out of these three, and which could be diagonal, vertical, or horizontal. If the best is diagonal, make it red. Okay, make it red, so that we can later on we can trace that how we got the best score. Did we get it through vertical move, horizontal move, or diagonal move? If it is diagonal, it should be red. Okay. Now we are going to use this for scoring the alignment. Now you understand? Okay. So I am going a bit faster, but let me know if you are not able to understand. Okay. So, but first we have to set some boundary conditions. For example, if I is equal to 1 and j is equal to 1, then this would be F00, right? And you would wonder what F00 is. So let's see actually the alignment of two sequences, and just two residues of the two sequences are shown. So Fk is aligned, so Fk is sequence 1 and Fm is sequence 2. Okay, so Fk is aligned to Fm. So what are the indices here? So this is position index 1. So this would be position index, this one, the gap. So if this is 1, this is 2, what is this? 0, right? And similarly, this is also 0. So 0th position in first sequence and 0th position in second sequence. So this is F00, right? And gap aligned to a gap doesn't make any sense because residue is aligned to a gap, right? So it doesn't make any sense, and you can say that the F00, which is the best score up to position 0 in sequence X and 0 in sequence Y, is 0, right? So this way you define the first boundary condition F00 is 0. Okay, so here is the matrix. So this is first position in sequence 1, second position in sequence 1, first position in sequence 2, and second position in sequence 2. And this is the 0th position in sequence 2, 0th position in sequence 1, right? So you have to fill each of these cells with the best score up to that position. Okay, so this is F00. F00 is 0. Okay, now next consider this one. Fk is aligned to Fm this way. Okay, so what are the indices here? So for first sequence the index is 0, for the second it is 1. Okay, so where is 0, 1? So 0 in first and 1 in second. So this one, right? So this position. So let's focus on this position. So what is the best score up to this? So best score up to this can be obtained from best score 1 position back, which is 0, and then increment it with the gap penalty. So gap penalty is -2. So 0 minus 2 minus 2. So I am going to fill this with -2. Okay. So if you repeat this, then the next would be -4. Then next would be -6 and so on. Okay. And then for this also it would be 0, -2, -4, -6, -8 and so on. So thus you have filled with the boundary conditions that we are setting up for this matrix. Okay. So these the first row and the first column has got filled up. We did it by setting up the boundary condition for this recursive equations. Okay. Okay. So now look at this. If you know, so these are given to you. If you know these, then you can get this, right? You can compute and you can get this, which means that if you know these three, you can get this, right? Okay, very good. And then you have to see which move is giving this value, and then you make that move red, and we will do it. So, okay, we have filled this up. So, which means that if we know these three, we can compute this, right? Best score that we can fill here. Same thing. If we know this, we can get this, right? From here. If we know this, then we can get this. Maximum out of the three. Okay, let's do it. Let's consider the diagonal move. So, diagonal means match. Okay, match or mismatch. So what is here? So, let's look at this cell. F. Is it match or mismatch? Match. Okay, match. Okay, so 0 plus, what is the score for match? Plus 1. So 0 plus 1, plus 1. So I am going to write plus 1. Okay. Then this is vertical. Vertical is gap, and gap gets a score of -2. So -2 plus -2, -4. So I am going to write -4 here, and then similarly the horizontal move. Okay. So horizontal is also gap. So -2 plus gap penalty -2, which is -4. Okay. So now you have the scores for the three moves: -4, +1, -4. For these three moves, you have to get the best out of this, or the maximum out of this. So what is the maximum out of these three? +1. So you are going to fill this cell with +1. Okay. And you will make this move that led to +1 red, and that move is diagonal move. Clear? So now you have filled this up. You can fill this because you know these adjacent values, right? If you know the values for these adjacent cells, you can get the best score for this cell, and we will do it. Okay. So now we know these values, we can fill this up. So consider the three scenarios diagonal, okay, -2. So diagonal means what? Match or mismatch. So what is this? Match or mismatch? No, it's diagonal, of course. Mismatch. F is aligned to M, and that will get a score of -2. So -2 plus -2, -4. So we'll put -4 here. And then this is vertical, which is a gap. So -4 plus -2, which is equal to -6. And then horizontal, also a gap. So +1 plus -2 is equal to -1. So which is the best out of these three? Which is the maximum out of these three? -4, -6, -1. -1. So I will fill this with -1. Okay, now repeat this, and you would have filled. So here are the two sequences, sequence 1 and sequence 2. You would have filled it, and you would come to the last, which is the best score of the alignment. -4 is the best score that you can get for the alignment of these two sequences. Okay. So the whole idea was to get the best score up to a certain position in the alignment of two sequences by extrapolating from the best score one position back, and then consider the three scenarios and then extend it, keep extending it to the end. Okay, when we did, we get the final score, the best score, which is -4, but yet we don't know what is the optimal alignment, and for that you will have to trace back. How did you get -4? Okay, so let's look at this. How did you get -4? And these red lines, these red arrows are indicating how you have got the best scores in a certain cell. Once you have reached the end, and this is the last cell, actually the last residue positions for the two sequences. So you got -4, and then you have to trace back. How did you get -4? Is it vertical move, horizontal move, or diagonal move? Diagonal, right? So diagonal. So diagonal means match or mismatch. So let's look at the residues E, E. Okay, so E aligned to E. Okay, so now I am here. Okay, how did you get -5? Which move? Vertical, horizontal, or diagonal? Horizontal. Horizontal. So horizontal means that you move. Yeah, horizontal means that gap, and then you will say that okay, it means that you move from residue L to N in sequence 2, but you remained at residue L in sequence 1. Okay, the residue that you move to should be aligned to a gap. Okay, this rule we already discussed. So which residue you move to? N. So N in sequence 2 should be aligned to a gap, right? Okay, now I am here. How did you get -3? Diagonal. Diagonal. So look at so which is match or mismatch. So then look at what residues are there at this location. L, L. So L should be aligned to L. Okay, and then I am here. So how did you get it? Again diagonal. So P aligned to P. P aligned to P. So now I am here. How did we get it? Okay, horizontal. Horizontal means that you move from you move from D to T in sequence 2, but you remained at D in sequence 1. So the residue that you move to should be aligned to a gap. So T in sequence 2 should be aligned to a gap. So now you are here. Okay, how did you get -4? Okay, -3. Okay, sorry, yeah. So -3. So how did you get -3? Diagonal. So what is the alignment going to be? So D, D. So D aligned to D. So now I am here, -4 here. How did you get -4? Vertical, which means that you moved from residue M to E in sequence 1, but you remained at residue D in sequence 2. So which residue should be aligned to a gap? E in sequence 1 should be the residue that you move to should be aligned to a gap. So E in sequence 1 should be aligned to gap. Okay, and then this is diagonal. So M is aligned to M, right? And then you are here. This is vertical, and vertical means that okay, K to H, but you remained at F. So H should be aligned to H in sequence 1 should be aligned to gap, right? And similarly, now you are here. So K in sequence 1 should be aligned to a gap, and then diagonal finally F is aligned to F. Okay. So this is trace back. So once you have computed the matrix, you can trace back and you can obtain the optimal alignment. Okay. So this is the optimal alignment. So this is dynamic programming algorithm. This is both mathematical and computational, but this helps you in solving a biology problem. Okay, without doing so many computations, it is just not possible to do this naively because of the computational demand that it would impose if you do it naively, like lining up all possible sequences and then scoring them one by one. This dynamic programming algorithm, where you just extended the best score starting with the beginning, then towards the end you obtained the best score for the last positions, and then you trace back to obtain the optimal alignment of the two sequences, right? Okay, so yeah, this was used for aligning the entirety of the two sequences. And that method is called global sequence alignment, developed by scientists Needleman and Wunsch, also called Needleman-Wunsch algorithm. So consider two sequences, and when they were aligned, the identity computed for them was 15%. Okay. On the other hand, if you consider regions delimited by these vertical lines, and if you just compute the alignment score for that region, you will see that it's 30% identity, which is double of the 15% identity from global alignment. So which means that there are regions within sequences that are more conserved than the entirety of the sequences. Okay. So and that is important because those regions are actually the conserved regions. They are critical sites within structures, and those sites are responsible for functions of the proteins. So often you would want to identify those regions, they are called domains, and if you perform global alignment, then you are not focused on identifying those domains, those regions. You are focused on just getting the best alignment for the two sequences, considering the entirety of the two sequences, which means that even if you get negative scores, you keep extending it. On the other hand, if there are regions that are highly conserved, you would not expect negative scores, right? You would expect positive scores because you are looking for conserved regions. And that cannot be solved using global alignment algorithm, because in global alignment algorithm, you are constraining due to the condition that the entirety of the sequence should be aligned. So you are not focused on regions, you are just focused on the entire sequences. And that is why you have the negative scores and you have kept extending it, because you want to get the best alignment for the entirety of two sequences. And due to this reason, you may not be able to identify domains in sequences using global alignment algorithm. So for that, local alignment algorithm was developed, and it is called Smith-Waterman algorithm, where the whole idea was that if you get negative score, make it 0, because you want to identify conserved regions. Conserved regions will have positive scores. So you should have a third equation also, 0. So if the best of these three, first to three is negative, then the best of negative and 0 would be 0. Okay, which would mean that if you encounter negative scores, make it 0. So you can see that all the boundary conditions, they have now 0 values. Okay. So using this equation, you can find domains. So do similarly as I showed you how to do. You will be given the rules, which means the score for match, score for mismatch, score for gaps. You will use and fill it up. Okay. If you encounter a negative score, make it 0 and start afresh. And thus you would have filled up this score. Once you have filled up, you have filled up this matrix. Once you have filled up the matrix, then identify the best score in the matrix. Okay. And then you trace back. So the best score in this matrix is, look for the best score in this matrix. Can you see the highest score in this matrix? 3 by red color coding. Okay. So 3 by 3, and then you trace back. So you get 3.3 by which move? Diagonal, vertical, or horizontal? Diagonal, diagonal, and diagonal means that G should be aligned to G. How did you get 2.3? Diagonal, which means U should be aligned to C. 2.7, this is also diagonal, U should be aligned to U. This is 1.7, this is vertical. Vertical means that A should be aligned to gap. Very good. A should be aligned to gap. Very good. And this is diagonal. So C should be aligned to C. Again diagonal. C should be aligned to C. And this is also assuming that this is coming from here. So I would say diagonal. So G should be aligned to G. When you are tracing back and when you hit 0, done. Okay. Stop there. So thus you have, once you trace back and thus you are aligning, you have got the local alignment of the two sequences. Okay. And thus you would have computed the scores as well as percent identity, percent similarity, all these different metrics. Okay. So let me see the time, and I think Dr. Shukla will do tutorial today. Okay, yeah. So yeah, he is going to do maybe 1 hour of tutorial, and tomorrow the first 2 sessions will be by Dr. Shukla, and I will join in later during tutorial, and we will do tutorial for today actually. So my questions that I was thinking of discussing with you today and tomorrow, so we will do both tomorrow. Okay. But Dr. Shukla has something really very interesting that he would want you to try on today. So he will come now and he will have his tutorial. Okay.
So you can take a break of 5 to 10 minutes. Then we start doing final break for the day. So this session, leak on कर दिया आपने या नहीं किया? जो start leak is on. चलने दो. ये pause करके फिर next week.